Hello class, my name is Brian Jimenez and today I will be presenting to you guys the method of finding the least common multiple and the greatest common factor. And I will be doing this via this board, which hopefully you guys could see properly. My apologies if it's not good enough, but I'll try my best. So what is the least common multiple, or the LCM? The LCM of two integers is considered to be the smallest positive integer that is a multiple of both given integers. So basically the smallest multiple. It's a straightforward least common multiple, smallest multiple. So I will be showing you guys exactly how you could find it. And with this first example, I'm gonna show you guys with simple numbers. So determine the LCM of 3 and 4. So for simple numbers such as 3 and 4, all we have to do is just write down. Hopefully you guys can see that. Let me extend my screen a little bit. Okay. So all we have to do basically is write down the multiples of each number until we actually find one that matches for both of them. So we are gonna try with 3 and then with 4. So with 3, the multiples of 3, well, let's start it off. So it'd be 3, 6, 9, and 12. So let's stop right there. So now we're going to move on to 4. So with 4, the multiples of 4 would be obviously 4, 8, and 12. And as you guys can see, what we have in common is that both numbers have the multiple of 12. And that is the first multiple that is given for both 3 and 4, meaning that the least common multiple of 3 and 4 is 12. So let me just erase this very quick. I don't actually have an eraser myself, so I'm gonna have to try to do this with my finger. Hopefully it doesn't mess everything up, but my apologies. Okay. So example number 2. So this example has numbers 35 and 50, and as you can see, those are obviously bigger than 3 and 4. But a clue with finding the least common multiple is not just finding them via like writing down the multiples, but with bigger integers, one can use the highest numbers of the prime factorization of both numbers to find the least common multiple. In in other words, for both 35 and 50, since they're both big numbers, what we're gonna have to do is first start off with finding the prime factorization of both numbers. So let's start off with finding the prime factorization of 35. So the multiples of 35, or the numbers that make up 35, would be 5 and 7. And as you guys could see, 5 and 7 can't be divisible by any other numbers than 1 in itself. So therefore, the prime factorization of 35 is either 1 times 35 or 5 times 7. And now the prime factorization for 50. So let's start off with the bigger numbers. So it'd be 2 and 25. Okay. So 2 can't be divisible by any other number other than itself and 1. So that's already as it is. But with 25, it goes down to 5 times 5. And after 5 you can't divide that by any other number, meaning that the prime factorization of 50 is 2 times 5 times 5. So now we're going to write that down in an orderly fashion. So 35 is basically 5 times 7. And 50 is basically 2 times 5 times 5. But in order to make our notes more simple, we're going to write it as 2 5 square with the power of 2, since basically 5 to 5 square root 2 is, I'm sorry, 5 to the power of 2 would be 5 times 5. So let me write it out for you. This would basically be the same thing as writing 5 2. So whenever we're finding the LCM for bigger numbers, what we have to do is basically use the highest prime factorization of all the numbers. So we're gonna start off with 2. So as you guys can see, there's no other 2. So basically we're gonna use this 2 right here. And then we move on to the next number, which is 5. So from 5, basically 5 is the same thing as 5 to the power of 1. So we're going to keep it as 5 to the power of 1. So which one would obviously be bigger, 5 to the power of 1 or 5 to the power of 2? Obviously 5 to the power of 2. So then we're going to write 5 to the power of 2. And then after that, all we're left is 7. Since there's no 7 on this number for 50, 7 to the by itself, or 7 to the power of 1, is the highest prime factorization of both numbers. So we're going to write it next to here. So now is where we find our final step. After we find the prime factorization and the highest prime factors of both numbers, we have to multiply our results in order to find the least common multiple. So in other words, we have to solve for this. So 2 times basically 5 to the square root, 5 to the power of 2 is what? 5 times 5, which means it is 25. So 25 times 7. So let's start off. 2 times 5, basically that makes 50. Times 7, 50 times 7 would basically be 350, because let's say we remove the 0 or cover up the 0. 5 times 7 is 35, but we still have that 0, so we add it in, meaning 350. So in other words, the least common multiple for 35 and 50 would be 350. Okay, my apologies. So why is it used and why it works? So basically finding the least common multiple could be used to make it easier to add fractions that contain different denominators. For example, 1 over 2 and 1 over 3 can basically be translated using the least common multiple as 3 over 6 and 2 over 6, since 6 is obviously the least common multiple of both 2 and 3. Okay, now we're going to move on to the greatest common factor. So what is the greatest common factor? The greatest common factor, or the GCF, of two numbers of 2 or more integers is the largest positive integer that divides the given numbers without a remainder. So we're going to start off with this example, determining the greatest common factor of 24 and 60. So what we need to do in finding the greatest common factor of two numbers is find the prime factorization for both of them, which is our first step. So we're going to start off with 24. Let's start off with the prime factorization. 2 times 12 is 24. 2 can be divided by anything else other than itself in 1. So we're going to leave it as that. Then 12 times 2, 12 could be basically divided by 6 and 2. 2 can be divided by anything else and other than itself and 2. And then we have 6, which could be divided by 3 and 2. And since nothing else could divide 3 and 2, what we have as a prime factorization for 24 is 2 times 3 times 2 times 2. Now let's move on to 60. Okay, so we're going to do 2 times 30. 2 can, obviously, like how I mentioned over here, it can be divided by anything else, so we're going to leave it at that. And then with 30, it could be 2 times 15. 2, like I said, leave it as that. 15, 5, and 3. 3 over here was basically left on its own, so we're going to do the same thing here. And with 5, also the same thing, because it can be divided by anything else other than itself and 1. Meaning that the prime factorization of 60 is 2 times 2 times 3 times 5. So then we're going to write that in an orderly fashion here at the bottom. So 60 is basically 2 times 2 times 3 times 5, and 24, my bad, 24 is basically 2 times 2 times 2 times 3. Okay, so what now? Basically, to determine the greatest common factor of both of these numbers, what we have to do is find out in both prime factorizations like where they overlap. So from these numbers, we could see that what they have in common is both of them have two twos. They have this, they have that. There's no extra two for 60, so we're only gonna underline two twos for 24. And then what else do they have in common? We see that they also have a 3. So we're going to underline the 3. Everything else that isn't underlined means that it doesn't have like they don't have each other in common. Therefore, they don't matter in this current situation. So now what we could see is that they have this in common. 2 times 2 times 3. So then our final step in order to find the greatest common factor is to basically solve for this. So 2 times 2, 4. 4 times 3 is 12. And like that is how we find the greatest common factor for both of these numbers. 12 is the greatest common factor for both 60 and 24. Now just give me 1 second while I erase this because my eraser is pretty small. Like I said, my apologies. So now we're going to move on to a bit more challenging problem, which I even had personal issues with it. And this number would basically be determine the greatest common factor of 25 x to the power of 3 and y to the power of 4 and 15 x to the power of 2 with y to the power of 2. So let me write these down very quick for you guys. It's basically 25 x3 with y4 and then 15 x to the power of 2 and y2. So basically the first step to solving these is doing the same thing that we did with the previous problem. So we're going to start off first with the whole numbers. For now, let's just ignore these for the moment, okay? So we're going to do 25. So the prime factorization of 25, 5 times 5, can be simplified to anything else. So this is the prime factorization of that. For 15, same thing, 3 times 5, nothing else, leave it at that. And then with x to the power of 3 and y to the power of 4 and x to the power of 2 and y to the power of 2, we would just basically write it in an expanded notation. This would be basically x to the power of 3, x times x times x 3 times. And same thing with this one, y times y times y times y 4 times, x times x 2 times, y times y 2 times. So what I'm going to do for you guys is write it down underneath the right here. So basically this number is going to equal to this. So 25 x to the power of 3 to y to the power of 4 is going to equal 5 times 5 times x times x times x times y times y times y times y. And if there's any confusion as to how many I have to write, just look at what power it is. There's power to the power of 3, 3x's, to the power of 4, 4y's. And we're going to do the same thing for this number right here. So 15x to the power of 2 and y to the power of 2. How we already solved for it would be basically 3 times 5 times x times x times y times y. So this is where it gets much easier, because now we have everything written down in expanded notation. So now what we have to do is basically like the same thing we did with the previous problem with the other numbers. We have to see like within these prime factorizations like where they overlap and what they have in common. So as we can see, neither of them have a 3. I'm sorry. The like both of them don't have a 3. It's only 15 that has the that has a 3. But both of them do have a 5, but just one 5. So we have that 5 right there. And then let's look at the variables x and y. So we could see that with both of the numbers, they both have two x's and they both have two y's. Anything else that isn't underlined, we just don't even look at it. So now we just focus on whatever is underlined, which is 5 times x times x times y times y. So this right here is what we find in common with both of these numbers, the greatest common factor. But we can't just leave it written down like that. We have to basically solve for it. So these are just variables and not necessarily numbers. So we can't necessarily multiply 5 times this, but we would just leave it as 5x or 5y. But these can multiply on their own. X times x, it'd basically be x to the power of 2. Y times y, y to the power of 2. And this is this, but in a simplified version. And now we have found the greatest common factor of both 25x to the power of 3 and y to the power of 4, and 15 to the x to the power of 2 and y to the power of 2. Okay, why is it used and why it works? Finding the greatest common factor can be useful to simplify a fraction. For example, 27 over 36 can be simplified as 3 over 4, since after finding the prime factorization of 27 and 36, the greatest common factor of both of these two numbers is 9, and dividing both numbers by 9 simplifies the fraction down to 3 over 4. How I basically said, in other words, the greatest common factor to simplify a fraction, basically you find the greatest common factor of both 27 and 36, and we result in finding out for it to be 9. And once we divide both sides by 9, we simplify down the fraction to 3 over 4. So these are just a few examples and a few problems that you guys could practice on your guys' own. And I have listed them from the easiest to the most difficult for both the least common multiple and the greatest common factor. Thank you for your time.